So 3D vectors. This is much more complicated just in how it looks. It's really not any more complicated in how it behaves from a 3D Cartesian vector approach, except for that instead of just I and j, now we have I, j, and k. But if you look, the construction is all the same. We have three direction angles now, theta x, theta y, and theta z. Here's theta x, theta y, and theta z. Now, do realize, if you were to be able to spin this around in 3D space, these angles are not lying in any particular plane. They're not lying in the plane of the page. They're not lying in the XY plane. They're all swinging in the shortest angle possible from their respective axis to this vector, right? So if this vector is coming out into the positive x, positive y, positive z portion of space, like it is, theta x is swinging from the x towards us and up at the same time to get up here. And theta y is swinging towards us and down. And theta z is swinging away from us and up. So they're a little hard to actually see in real life, but they're not any harder to deal with on the page once you have Cartesian vector formats. That's why I was saying if it's hard to visualize the structure itself, the vectors that are going on, switch to this and just let the math do its work. The unit vector is then cosine of theta xi plus the cosine of theta yj plus the cosine of theta zk. So again, all three of these cosines and all three of those angles, those direction angles, are related to each other. If you know two, you know the other one because of this relationship right here. What's the magnitude of lambda? It's the unit vector. Its magnitude is 1. So you know that you should be able to take the square root of the sum of the squares of these three values and it should equal 1. So if you know two of them, maybe you know theta x and theta y, you can take the cosine of 30 degrees or whatever it is squared plus the cosine of theta y, which maybe that's 40 degrees squared, and then you can say plus cosine of theta z squared. Take the square root of all of that, and that's equal to 1. Solve for theta z. You can be able to solve for any of them. Again, if you know two of your direction angles, you always know the third, or at least can calculate the third. All right, here's a different way to look at 3D vectors. This one is very common in engineering. This is kind of like halfway 2D, halfway 3D, how we are showing this vector. In this, we know an angle, in this case, this angle phi is not one of the direction angles that we were just talking about. It's actually the angle in the xz plane to this line right here, which is the projection of this vector f down into the xz plane. So if the sun were shining directly above this vector, it would be casting this shadow, and this is the angle from the x over to it. Okay, and so you have to kind of follow the visual cues. We drew all these lines to help visualize where this is. If you wanted to find the y component of this vector, it's pretty easy because you could just take f times the cosine of theta y. You could then take f times the sine of theta y, which would give you this line up here, which is the same as this line down there, right? That line right there is the hypotenuse of a triangle in the xz plane. This triangle down here. And so the cosine of phi times whatever the magnitude of this line is here that we found would give you your x, and then the sine would give you your y. So again, you just got to think of triangles. Okay, so again, x is going to be the sine of theta y to get us this line right here, and then we're going to take the cosine of phi to get us that. That's why there's these two bits of trig. Fy was the easiest one, and fz is just going to be, again, we're starting with this line down here, right, by doing the sine of theta y, and then we're going to multiply by this edge over here over the hypotenuse to get the z component, so that's why it's sine phi times sine theta y times f. So this is an extremely common way that vectors are shown. Again, it's kind of halfway between 2D and 3D because it's showing some angles that are kind of like what we were dealing with in 2D and a little bit of your direction angles too. It's kind of halfway in between. Like I said before, the magnitude of a vector is the square root of the sum of the squares. I talked about it on the last slide about the unit vector. Here we know that the vector f's magnitude is going to be equal to the square root of the sum of the squares of all three x, y, and z components of that vector. Now in 2D, obviously, you know it's Pythagorean theorem. This is the Pythagorean theorem in 3D, basically. Square the x, square the y, square the z. Take the square root of all that, you get the magnitude. And again, that is also true for the unit vector. And that's how I was saying you could find those that third direction angle if you only knew two of them.